Thanks for joining me. We're on problem number 81 of Physics GRE GR0177. Which of the following is the orbital angular momentum eigenfunction YML of theta and phi in a state for which the operators L squared and LZ have eigenvalues 6h bar squared and minus h bar respectively? So big L squared is going to equal L times the quantity L plus 1, that all times h bar squared, and as the problem states, it equals 6h bar squared. So little l is going to equal 2. Big LZ equals mh bar, as again the problem states, equals minus h bar. And so m is going to equal minus 1. So yml of theta and phi is going to equal y minus 1, 2 of theta and phi. And that is going to be answer B. Number 82. Let the ket of alpha represent the state of an electron with spin up and ket beta the state of an electron with spin down. Valid spin eigenfunctions for a triplet state, 3s, of a 2-electron atom include which of the following? So our alpha ket is going to equal our spin up, is going to equal plus 1/2, is going to equal our little arrow going up. Our beta ket is going to equal spin down, equals minus 1/2, and that's our little arrow going down. And there are going to be 4 basis states: up, 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 down, up, and down, down. So states with spin equal to 1 are symmetric, and there are 3 states like this. 1, 1, which is the up, up, 1, comma 0, which is going to be our up, down, plus our down, up, divided by the square root of 2. And the 1, minus 1, which is our down, down. All of these are s equals 1, which is our triplet state. So for s equals 0, for our 4th state, and it is antisymmetric. It's our 0, 0. It's going to equal our up, down, minus our down, up. That all divided by the square root of 2. Again, it's the s equals 0 singlet state. So 1 and 3 in the selection choices, 1 and 3 are the triplet states, and 2 is the singlet state. So the beta 1 and beta 2 ket, similar to what this number 1 would be except with betas, that would also be the triplet state if listed, and but it's not. That is number 1 and number 3, number 1 and number 3, and that is answer D. Number 83, the state of a spin 1/2 particle can be represented using the eigenstates spin up and spin down of the SZ operator. So SZ up equals 1/2 h bar up, SZ down equals minus 1/2 h bar down. Given the Pauli matrix sigma x equals and then 0, 1, 1, 0, which of the following is an eigenstate of S of x with the eigenvalue minus 1/2 h bar? So let's just look at each of our normalized wave functions. Our psi of z and our positive z direction is going to be 1, 0. That's going to be our spin up. Psi of z in our minus direction is going to be 0, 1. That's our spin down. So psi x minus direction is going to equal 1 over square root of 2. 1 minus 1. That's going to equal 1 over square root of 2 up, spin up, minus spin down. That's going to equal 1 over square root of 2. Again, our up state was 1, 0, minus our down state, 0, 1. So it asks for minus 1/2 h bar in the S of x eigenvalue, and so that is going to equal answer C. Number 84. An energy level diagram of the n equals 1 and n equals 2 levels of atomic hydrogen, including the effects of spin-orbit coupling and relativity, is shown in the figure above. 3 transitions are labeled A, B, and C. Which of the transitions will be possible electric dipole transitions? So our selection rules for electronic transitions, we have delta L equals plus or minus 1, not 0. Delta M of L equals 0 or plus or minus 1. Delta MS equals 0, and delta J equals 0 or plus or minus 1. So for A, we have delta little l equals 0, delta j equals 0. Well, we cannot have delta little l equals 0. It has to be plus or minus 1, so A does not work. Let's check B. Delta L equals minus 1, delta J equals minus 1. That's good, that's okay. And for C, delta L equals minus 1, delta J equals 0, but delta J did not go from 0 to 0, so again, that's okay. And so A doesn't work, B and C work. And so that is going to be answer D. Number 85. One end of a nichrome wire of length 2L and cross-sectional area A is attached to an end of another nichrome wire of length L and cross-sectional area 2A. If the free end of the longer wire is at an electric potential of 8 volts and the free end of the shorter wire is at an electric potential of 1 volt, the potential at the junction of the two wires is most nearly equal to. So our resistance is going to equal rho times our length of the wire divided by the area. So our resistance R1 is going to equal rho times 2L over A. R2 is going to equal rho L over 2A, and R1 equals 4R2. So V equals IR, V1 equals 4V2. The net voltage drop equals the change in the electric potentials equals 8 volts minus 1 volt equals 7 volts. So each voltage drop contributes to this, so V1 plus V2 equals 7 volts. So 4V plus V equals 7 volts. Remember V2 equaled V equals 7 over 5 equals 1.4 volts. V1 equals 4V equals 4 times 7 over 5 equals 5.6 volts. Add those two up together, you see they're 7 volts. So you can calculate the potential at the junction from either the high potential side going down or the low potential side going up. So 8 volts minus 5.6 volts equals 2.4 volts. Either way you do it, it's going to get you to answer A, 2.4 volts. Number 86. A coil of 15 turns, each of radius 1 centimeter, is rotating at a constant angular velocity W equals 300 radians per second in a uniform magnetic field of 0.5 Tesla, as shown in the figure above. Assume at time t equals 0 that the normal n hat to the coil plane is along the y direction and that the self-inductance of the coil can't be neglected. If the coil resistance is 9 ohms, what will be the magnitude of the induced current in milliamperes? Note the rotating coils cut in and out of the magnetic field. So we have Ohm's law, I equals V over R, and our EMF, which is voltage, equals E, equals N times d phi of B divided by dt, where N equals the number of coil turns. So our magnetic flux, phi of B, equals the integral of B times dA, and initially at time equals 0, phi of B equals 0, so it starts as a sine function since sine of 0 equals 0. So phi of B equals B pi r squared times sine of WT, where pi r squared is the area of the circle and sine WT is how that area changes. So d phi of B divided by dt equals B pi r squared times the quantity W cosine WT, where E equals N times d phi of B divided by dt, and let's plug in some numbers, equals 15 times 0.5 times pi times 0.01 squared times 300 times cosine WT. And the induced current I equals V over R equals 0.225 pi cosine WT divided by the whole quantity divided by 9 equals 0.025 pi times cosine WT amperes equals 25 pi cosine WT milliamperes. And so that is answer E. Number 87. Two spherical non-conducting and very thin shells of uniformly distributed positive charge big Q and radius d are located a distance of 10d from each other. A positive point charge little q is placed inside one of the shells at a distance d over 2 from the center on the line connecting the centers of the two shells as shown in the figure above. What is the net force on the charge little q? Well, since the charge little q is inside a shell of uniform charge big Q in the left sphere, this will produce no net force on the charge inside the sphere. The symmetry of the sphere means anywhere inside has all the sphere's force cancel / net out, so we only need to consider the right sphere. Both charges are positive, so little q will be pushed to the left since like charges repel. So our force is going to equal 1 over 4 pi EO, that quantity, times QQ over R squared, where r is the distance between the sphere on the right and the charge little q. So r is going to equal 10d minus d over 2 equals 19d over 2. And so our force is going to equal QQ over 4 pi EO times the quantity 2 divided by 19D, that quantity squared. And so that's going to equal QQ over pi EO D squared 19 squared. It's going to equal QQ over 361 D squared pi EO. And it's going to be to the left, A. Number 88, a segment of wire is bent into an arc of radius r in subended angle theta as shown in the figure above. Point P is at the center of the circular segment. The wire carries current I. What is the magnitude of the magnetic field at P? So the Biot-Savart law is given right here, where L, big L, in this problem is the arc length. So the arc length of circles, S, is going to equal r theta in radians. And so the integral of dB is going to equal B, is going to equal UOI over 4 pi times the quantity theta over r. Answer C. 89, a child is standing on the edge of a merry-go-round that has the shape of a solid disc as shown in the figure above. The mass of the child is 40 kilograms. The merry-go-round has a mass of 200 kilograms and a radius of 2.5 meters and is rotating with an angular velocity of w equals 2.0 radians per second. The child then walks slowly toward the center of the merry-go-round. What will be the final angular velocity of the merry-go-round when the child reaches the center? And the size of the child can be neglected. So we're going to use our conservation of angular momentum. Also note that the merry-go-round is anchored to the ground, so we're going to have our final angular momentum equals our initial angular momentum. When the child stands in the exact center, remember, as the problem states, the child is a point mass. You can neglect the size. So the child won't contribute to the angular momentum. So it would just be the angular momentum of the merry-go-round, where LF equals IWF equals, and the mass of the merry-go-round is going to be the big M. So big M, r squared over 2, that quantity times WF, the final angular velocity, which is WF. But for the initial angular momentum, we must consider the fact that the child is at a distance of r. So Li is going to equal I times W by, and that's going to equal big M r squared over 2 plus little m r squared, that whole quantity times Wi. And the moment of inertia of a point mass, again, that's our one right here, mr squared. And the moment of inertia of a disk is going to equal 1/2 mr squared. And the big M right here is our disk mass. So let's follow this through. Big M r squared over 2 times WF equals big M r squared over 2 plus little m r squared, that whole quantity times Wi. So again, we were given some of our numbers in the problem. We can plug them in now. So WF equals 2.8 radians per second, and that is answer E. Number 90, two identical springs with spring constant K are connected to identical masses of mass M as shown in the figures above. The ratio of the period for the springs connected in parallel, figure 1, to the period for the springs connected in series, figure 2, is, so let's just do a quick side note, where springs in parallel, the K equivalent is going to equal K1 plus K2, where springs in series, 1 over K equivalent, is going to equal 1 over K1 plus 1 over K2. Okay, so we know for simple harmonic motion, T, the period, equals 2 pi times the square root of M over K, where K is our spring constant and M is our mass. So for figure 1, KEQ, the equivalent K, spring constant, is going to equal K plus K equals 2K. For figure 2, the equivalent K is going to equal 1 over K equivalent equals 1 over K plus 1 over K, so 1 over K equivalent is going to equal 2 over K, where K equivalent equals K over 2. So then we can plug in these numbers to our simple harmonic motion. So T1 over T2, and that is going to equal 1/2, and that is answer A.